Welcome to Curiosity, the podcast where science meets wonder. Join us as we explore the fascinating, the innovative, and the unexpected, from the secrets of the cosmos to the marvels of everyday life. Each episode takes you on a journey to uncover the knowledge and stories that fuel our endless quest for understanding. Let your curiosity guide you.
Imagine if you can, just standing on the edge of this vast dune field.
Right.
But you have to push the image of the Sahara out of your mind. This isn't yellow sand against a bright blue sky.
Not at all.
The ground beneath your boots it's the color of dried blood.
Yeah, that rusted iron just stretching out.
Exactly, as far as the eye can see. And you look up, and the sky isn't that comforting azure you've known since you were a kid. It's a hazy, dusty, almost a salmon pink color. And the sun just looks a little too small.
A little too faint.
Yeah, hanging in that alien sky.
And it is quiet.
So quiet.
That's the part that really unnerves people in the simulations.
Yeah.
It is dead quiet.
There are no birds, there's no wind rustling through leaves, no distant hum of traffic, just absolute silence. And cold. We are talking colder than Antarctica in the dead of a sunless winter.
Easily.
And most importantly, and this is the part that really kills the mood, you cannot breathe.
No, definitely not.
In fact, if you were to, say, panic and rip your helmet off, it wouldn't just be suffocation you'd have to worry about. The physics of the place would literally cause your blood to boil inside your veins within seconds.
That is quite the cheerful image to start our deep dive with today.
I try to set the scene, but this is the reality we are dealing with. That is Mars today. It is a rusted, frozen, irradiated tomb of a planet. It's hostile in ways that our biology can barely comprehend. And yet, humans have this absolute unshakable obsession with it.
We really do.
We look at that dead rock and we don't see a graveyard. We see a blank canvas.
We see the ultimate fixer-upper.
Exactly. We see a dream that refuses to stay in the night. We imagine taking that cold vacuum and engineering it. We dream of thickening the air, warming the surface, coaxing liquid water back into those ancient riverbeds. We want to see the red turn to green and blue. We want to give humanity a second home.
Which we call terraforming.
Earth-shaping.
It's a concept that feels incredibly modern, doesn't it? Like something that was invented in a Silicon Valley boardroom in the last 10 years by some tech billionaire looking for the next big IPO.
It feels very Elon Musk. Very SpaceX Starship presentation.
It does, but it's actually surprisingly old. The word itself, terraforming, was coined way back in 1942 by a science fiction writer named Jack Williamson.
Wow, 1942.
Yeah, but the concept has been championed by serious scientists for nearly as long as the fiction writers. You had Carl Sagan, the great communicator of science, proposing models for it in the 70s. You have Kim Stanley Robinson, whose Mars trilogy is basically the sacred text for anyone who loves this idea.
I've actually read that trilogy, and it's incredibly detailed. It makes you feel like, oh, we could just go do this tomorrow.
Right.
It feels less like a novel and more like an instruction manual.
And that feeling, that sense that this is just a big construction project, just a matter of moving dirt and gas around, is exactly what we need to interrogate today. Because in this deep dive, we are unpacking the source material called the Red Blueprint.
Which is a massive collection of data.
It is. We have a stack of sources here, some really dense, fascinating papers on atmospheric physics, planetary geology, and even ethics. And we are going to answer the core question, not can we imagine it? We know we can imagine it.
We have great CGI for that.
Exactly. The question is it actually achievable?
Right, given the laws of physics, not the laws of narrative.
That's likely. Given the laws of thermodynamics, gravity, and chemistry, can we turn Mars into Earth 2.0? And I'll give you a spoiler alert right now. The answer is not a simple yes or no.
It never is.
It's a complicated, messy, fascinating journey through the absolute limits of human capability. It goes from absolutely impossible to maybe partially doable back to morally terrifying very quickly.
So if you're listening, buckle up. We are going to look at the hostile reality of Mars today, really shattering that romance. Then we'll look at the specific engineering hurdles of the atmosphere and magnets, which are way harder than I thought. And finally, the massive ethical dilemma of rewriting an entire planet's history.
Let's get into it.
Okay, first things first. We need to do a reality check. I think a lot of us, me included, honestly, have this red planet romance. We see the high-res photos from the Curiosity rover or Perseverance, and it looks like a desert in Arizona or Utah.
Very familiar terrain.
Yeah, it looks familiar. You think, okay, it's just a little dry. Let's bring a hose, plant some trees, maybe wear a jacket, and we're good.
And that familiarity is the most dangerous trap in planetary science. Because Mars is not Arizona. In detail, it is almost incomprehensibly hostile to life as we know it. It's not just hostile like a desert. It's hostile like the inside of a microwave inside a freezer.
So hit me with the numbers. Let's break this down. Why can't I just go plant a pine tree there right now?
Well, let's start with the atmosphere. On Earth, you and I are used to a thick blanket of air. It pushes down on us with a certain weight, what we call 1 atmosphere of pressure. It's about 14.7 pounds per square inch.
Right.
We don't feel it because we evolved in it, but it's heavy. It literally holds us together. Mars, its atmosphere is about 1% as dense as Earth's.
1%.
1%. It is, for all intents and purposes, a vacuum. You are dealing with pressure so low that it creates what physicists call the boil or freeze problem. Or, if you want to be technical, we are skirting the Armstrong limit.
The Armstrong limit. I mentioned the blood boiling earlier, which sounds like a B-movie horror trope, but this applies to water on the ground too, right?
Yeah. This is basic physics that we just don't often think about because we live in a pressurized environment. For liquid water to exist, you need pressure holding the molecules together. If the pressure drops too low, those molecules just fly apart. They boil into vapor, even if it's freezing cold.
That is just wild to think about. Cold boiling.
Exactly. On Mars, the average surface pressure is about 600 pascals. Earth is roughly 101,000 pascals.
Wow.
So at 600 pascals, liquid water is physically unstable. If you poured a cup of water on the Martian ground right now, it would instantly boil away into gas. But because the temperature is also brutal, whatever droplets didn't boil would instantly freeze into ice.
So it's physically impossible to have a lake on Mars right now, not because there's no water, but because the physics of the air won't allow it to exist as a liquid.
On the surface, yes, completely impossible.
Yeah.
And then you have the temperature itself. The average is minus 55 degrees Celsius.
Which is brisk.
It's colder than your deep freezer.
Mm-hmm.
But that average hides the extreme swings. At the poles, in winter, it drops to minus 125 degrees Celsius. That is cold enough that carbon dioxide, the gas we breathe out, freezes solid. It literally snows dry ice on Mars.
Oof, that's hard to wrap your head around.
And even if you go to the equator, let's say you take a little vacation to the Martian tropics. On a summer day at noon, the temperature might actually hit 0 degrees, maybe even a delightful 20 degrees Celsius. You might think, hey, t-shirt weather.
I'm back in my bags.
But don't, because the moment the sun sets, the temperature plummets well below minus 70 or minus 80. Why? Because that thin atmosphere provides 0 thermal buffering.
It's like being on a really high mountain, but worse.
Exactly, but multiplied.
Yeah.
On Earth, our air holds heat like a thick wool blanket. Mars has no blanket. It's a vacuum flask that's been broken. So the temperature swings are violent and immediate. You go from brisk autumn day to instant death in a matter of hours.
Okay, so we have a vacuum, we have freezing cold. What about the radiation? I know Mars doesn't have a magnetic field like Earth does.
That's the invisible killer. Earth has a molten metal core iron and nickel swirling around deep underground. That movement generates a massive magnetic field that surrounds our planet. That field acts like a shield, deflecting the solar wind and cosmic rays. Mars lost its magnetic field billions of years ago. We think its core just cooled down and solidified.
So the shield is down.
The shield is totally down. The surface is continuously bathed in cosmic radiation from the galaxy and solar particles from the sun. Estimates suggest the radiation levels are roughly 40 to 50 times higher than on Earth, and that's just the baseline on a calm day.
And if the sun burps?
If there is a solar flare or a coronal mass ejection, you're getting hit with acute radiation poisoning. If you were standing on the surface in a normal spacesuit during a big event, you could die within days or weeks. It basically sterilizes the surface.
And we haven't even talked about the dust. I was reading the source material on the soil chemistry, and this was actually new to me. I thought dirt was just dirt.
Oh no, the dust is nasty. It's not just sand, it's chemically reactive. It contains high concentrations of perchlorates.
Perchlorates. Sounds like something in a chemistry set I strictly shouldn't touch.
You absolutely shouldn't. They're highly oxidizing salts. They are toxic to the human thyroid. They totally mess with your hormones. They are toxic to most plant life. So the dirt itself is poisonous. If you tracked that dust into your habitat and you breathed it in over a few months, you'd get violently ill. And remember, Mars has global dust storms.
Right.
These aren't like the haboobs in Arizona. These storms can grow to engulf the entire planet for months at a time, completely blocking out the sun.
So just to recap the hostile reality segment before we get too optimistic about growing potatoes like Matt Damon, We have a poisonous, vacuum-sealed, irradiated, deep-freeze world where water boils and freezes simultaneously, and the air itself tries to kill you.
That is a fair and highly accurate summary. It is not a nice place.
But, and here is the big but that keeps the dream alive, it wasn't always this way. This is the geological tease, right? This is what drives the planetary scientists crazy.
It is the great mystery of our solar system. When we look at the photos from orbiters like the Mars Reconnaissance Orbiter, we see things that look undeniably like riverbeds. We see meandering channels. We see delta fans where rivers emptied into craters, leaving sediment piles exactly like the Mississippi Delta. We see minerals, clays, and sulfates that only form in the presence of liquid water.
So Mars was wet. That's an established fact.
Mars was wet. Mars was warm. Mars had a thick atmosphere. Mars had a magnetic field. Billions of years ago, roughly nearly 4 billion years ago, it was surprisingly Earth-like. It might have even been a blue planet.
So the concept of terraforming isn't actually creating something entirely new. It's restoration. It's asking if we can hit the rewind button.
Exactly. Can we do in a few centuries what nature undid over billions of years? And to do that, we have to solve what the sources call the atmosphere bottleneck. This is the single biggest engineering hurdle.
Let's unpack this bottleneck, because you said the atmosphere is the prerequisite for everything else.
It is. You cannot have liquid water without pressure. You cannot have warmth without a greenhouse effect to trap the sun's heat. And obviously you can't breathe a vacuum. So step one of any terraforming plan, before you plant a single seed, before you release a single microbe, is you have to get thick air.
Okay, so we need gas, lots of it. Where do we get it? The theory I always hear, and this is the one in the movies like Total Recall, is that we just melt the poles.
The just add heat theory.
Right. There's carbon dioxide frozen at the poles. There's CO2 locked in the dirt. If we just heat the planet up a little bit, maybe with giant mirrors, maybe with nukes, like some have suggested, that gas releases into the air. Then, because CO2 is a greenhouse gas, it traps more heat, which releases more gas.
A feedback loop.
A runaway greenhouse effect. It's what happened to Venus, but in a bad way. Here, we want it to happen.
It sounds perfect. The planet essentially fuels its own transformation. Free lunch.
It does sound perfect. It's an elegant solution, but science has a way of ruining perfect stories with hard math. We need to talk about the Joukowsky and Edwards reality check from the source material.
This sounds like a law firm. Injured in a terraforming accident. Paul Joukowsky and Edwards.
It really does. But it's actually a pivotal scientific paper published in Nature Astronomy in 2018 by Bruce Joukowsky and Christopher Edwards. Bruce Joukowsky was the principal investigator for the MAVEN mission.
MAVEN, right. The Mars Atmosphere and Volatile Evolution mission.
Yes, that's the NASA orbiter specifically designed to study the Martian atmosphere. They decided to do a serious inventory. They stopped guessing and looked at the hard data. They literally counted the molecules.
They checked the pantry to see if we actually have enough ingredients to bake the cake.
Exactly. They looked at the polar ice caps. They looked at the shallow minerals. They even estimated what might be deep underground in the crust based on radar and spectroscopy. They calculated how much CO2 is actually physically present on the planet.
And what did they find?
The pantry is almost empty.
Oh no. How bad is it?
Their verdict was stark. Even if you vaporized all the accessible CO2 on Mars, if you melted every single ice cap, baked the soil to release the gas attached to the dust grains, and released everything from the shallow crust, you would only raise the atmospheric pressure to about 1.5 to 2% of Earth's pressure.
Wait. Pause. Let me make sure I understand this. We need 100% for breathable air. We need at least 10% or 20% just to have liquid water stabilize so we don't have to wear a full pressure suit. And you're saying the total inventory gets us to 2%.
Maybe 2% if we are incredibly lucky. We're starting at around 0.6%, or roughly 6 millibars. Their analysis suggests that mobilizing all known accessible sources might triple that, getting us to maybe 15 or 20 millibars. That is nowhere near enough. It's barely a rounding error toward habitable.
So the gas just isn't there. Where did it go?
Most of it was stripped away by the solar wind over billions of years. It was literally lost to space. Some of it is locked up in carbonate rocks, but those deposits are buried incredibly deep and they just aren't as massive as we hoped. No. The easy fuel source for terraforming, the whole idea that Mars is just sleeping and waiting to be woken up, is a myth.
Well, that puts a massive damper on things. That feels like a project killer right there.
It's a massive problem. It means you can't just warm up Mars. You have to build an atmosphere from scratch. If the gas isn't on Mars, you have to bring it there.
Import it.
Import it. And this is where we get into the extreme alternatives the sources talk about.
Yeah.
Because the scale of importing an atmosphere is mind-boggling.
I've heard about crashing asteroids. That's the go-to sci-fi solution.
It is. The idea is you find asteroids or comets in the outer solar system, maybe out in the Kuiper Belt, that are rich in ammonia, nitrogen, and water ice. You strap giant fusion engines on them, and you steer them to crash into Mars.
It sounds very Michael Bay.
It's incredibly spectacular. But let's look at the logistics for a second. To get the amount of nitrogen and volatiles we need to make an actual difference in the atmospheric pressure, you aren't crashing one asteroid. You aren't crashing 10. You are crashing thousands.
Thousands.
Thousands of massive objects, each one potentially a dinosaur killer size. The energy required to move them from the outer solar system is beyond our current civilization's total energy output for centuries.
Yeah.
And then think about the impact itself.
Right, they hit hard.
When they hit, they release kinetic energy, immense heat. If you bombard the planet with thousands of asteroids, you aren't just delivering gas. You are turning the surface into a molten slag heap. You are sterilizing the planet completely. It would take centuries for the dust and heat to settle before you could even think about living there.
So we destroy the house to save the house.
Essentially, it's a violent, chaotic method.
Okay, let's scratch the bombardment idea. What about option B? Manufacturing gas. We are really good at making greenhouse gases on Earth. We accidentally warmed our own planet with them. Can't we do it on purpose on Mars?
This is the super greenhouse idea. It's probably the most scientifically plausible path. We could build factories on Mars to pump out special gases, specifically CFCs or perfluorocarbons. These are super gases. One molecule of a CFC can trap thousands of times more heat than a molecule of CO2.
Highly efficient.
Very efficient. But here's the catch. You need to build an industrial infrastructure on Mars that dwarfs anything on Earth. You need to mine the fluorine and the chlorine. You need massive nuclear power plants to run the factories. And you can't just do it once.
Why not?
Because sunlight destroys these chemicals. UV radiation breaks down CFC, so you have to keep producing them. Constantly. Forever.
It's a subscription service model for a planet.
Yes. Mars Prime. If you stop paying the energy bill, the heat turns off and the atmosphere collapses back into the dirt.
And this brings us back to that other problem you mentioned earlier, the magnetic field, or the complete lack of one. Because even if we build this massive atmosphere, nature is actively trying to take it away.
The Sisyphus problem.
Right, pushing the boulder up the hill. Mars has no magnetic shield.
Correct. The reason Mars has such a thin atmosphere today is largely because the solar wind, that stream of charged particles from the sun, stripped it away over billions of years. It crashes into the upper atmosphere and just knocks atoms off into deep space. It's a process called sputtering.
So if we go through all the trouble of importing asteroids or building these planetary factories, the sun is just going to eat our lunch anyway.
It will try. Now, to be fair to the math, the stripping process is incredibly slow. It takes millions of years. So on a human timescale, it's not like the air would vanish overnight. But it adds to the philosophical sense that terraforming is never truly done. It is always an active maintenance project.
Unless we fix the leak.
Unless we fix the leak.
Can we restart the core? Like in that movie, The Core, can we jumpstart the planet's heart?
No. That is pure fantasy. The energy required to melt a planetary core is, well, it's physically impossible for us. But there is a proposal for an artificial shield.
Do tell.
It comes from Jim Green, a former chief scientist at NASA. The idea is to build a massive magnetic dipole, basically a giant electromagnet, and park it in space, specifically at the L1 Lagrange point.
That's the gravity balance point between the sun and Mars.
Correct. It would sit roughly 1 million kilometers upstream between the sun and Mars, and it would generate a magnetic field strong enough to deflect the solar wind around the planet.
It would cast a magnetic shadow.
Exactly. It would act like a windbreaker or a giant umbrella. Mars would sit in the safety of this wake. The atmosphere would stop stripping away. And actually, as the atmosphere thickened naturally from regular volcanic outgassing over time, it would stick around.
Is that even possible?
Physics says yes. Engineering says, are you out of your mind?
Why? Just the size of it.
The scale is absurd. To generate a field that big, you need a structure in space that is massive. We are talking about superconducting coils that might be kilometers wide, powered by dedicated nuclear reactors maintained in deep space forever. It's theoretically possible, but practically audacious. It's something a Type 2 civilization on the Kardashev scale might do. We are barely Type 0.7.
We're still figuring out how to keep the Wi-Fi on in the subway.
Precisely, and here we are talking about planetary engineering.
So we have the atmosphere problem, not enough gas. We have the magnetic problem, no shield. But there's one more physical hurdle that I think people forget when they picture a green Mars. Sunlight. Mars is further away.
It is about 50% further out from the sun than Earth. It only receives 43% of the sunlight Earth gets.
That's a huge drop, less than half.
It is. Imagine a heavily cloudy day on Earth versus a bright sunny summer day. Mars is permanently dimmer. This means that even if you somehow imported the exact same atmosphere as Earth, Mars is going to be significantly colder. It just receives less energy input.
So we need way more greenhouse gases than Earth just to get to the same baseline temperature.
Or we need space mirrors.
Mirrors, of course.
This is another classic proposal in the terraforming literature. You put giant, ultra-thin mirrors in orbit to reflect extra sunlight onto the surface. You could focus them on the poles to help melt the ice, or focus them on specific cities to provide local light and warmth.
How big are we talking for these mirrors?
Hundreds of kilometers wide. Imagine a mirror the size of Texas, made of aluminized mylar floating in orbit.
The engineering list just keeps getting longer and more terrifying. Asteroid tugboats, planetary-scale factories, artificial magnetic shields, Texas-sized mirrors. This really brings me to the concept of deep time that the sources emphasize, because none of this happens quickly.
This is the hardest part for the human brain to grasp. We are wired for short-term thinking. We worry about 4-year election cycles, quarterly earnings reports, maybe a 30-year mortgage if we're really stretching. Terraforming is a project for deep time.
How long is deep time in this context?
The warming phase alone, just getting the pressure up and the ice melted using these mega projects under the most optimistic scenarios, is centuries. 300, maybe 500 years.
And that's just to get it wet and warm, not breathable.
Correct. The biological phase, making the air breathable so you can take off the mask, that's millennia.
The source material compared it to the Roman Empire.
Yes. The Roman Empire lasted roughly 500 years in the West. A terraforming project requires a continuity of purpose, funding, and technology that lasts longer than the Roman Empire.
Think about that for a second. Can you imagine a government project started by Charlemagne being consistently funded and finished today?
It's almost inconceivable. Human institutions rarely last that long. We change governments, we change our cultural priorities, we have wars. To commit to a 1,000-year engineering project requires a stability we have never once demonstrated as a species. It requires cathedral thinking, starting a project you know you will never live to see finished.
It's a really sobering thought. But let's say, just for the sake of argument, we are stubborn. Humanity unites. We transform into this enlightened species. We stick with it. We solve the heat. We solve the pressure. Now we need the living part. We need water and biology.
Well, the good news is water is the one thing Mars actually has in abundance.
Finally, a win for the terraformers.
It's not liquid on the surface right now, but it's absolutely there. The polar ice caps are massive. There is ground ice permafrost spanning across huge swaths of the planet. And, as we touched on, the Mars Express orbiter has given us incredibly strong evidence of subglacial lakes.
Liquid water underground.
Yes, deep beneath the South Pole. Kept liquid by the immense pressure of the ice above it and likely some geothermal heat leaking up from below.
So if we warm the planet with our supergases and space mirrors, that water comes to the surface.
Eventually, yes. If we melt the ice caps, we could cover the planet in an ocean tens of meters deep. It wouldn't be as deep as Earth's oceans. Earth is a true water world. But it would be enough. You'd have shallow seas, you'd have a vast northern ocean, you'd have a water cycle with rain.
Okay, so we have water. Now, can we just sprinkle the seeds? This is the green dream. I imagine retrofitted planes flying over these new oceans, dropping seeds, and forests springing up.
Biology is our best tool, but it is incredibly slow. We have to look at extremophiles first. Organisms that love extreme, awful conditions.
Like what?
Lichens, algae, and the absolute heavy hitter of the microscopic world. Cyanobacteria.
The bacteria that literally changed Earth.
Yes. Billions of years ago, Earth's atmosphere had basically no oxygen. It was mostly methane and ammonia. Cyanobacteria evolved, started photosynthesizing sunlight, and pumped oxygen into the air as a byproduct. They terraformed Earth for us.
So we just pack them onto a rocket, send them to Mars, and say, do your thing, little guys.
We can. Lab tests on the ISS and on Earth show some of them, like Crocoxidiopsis, can survive simulated Martian conditions. They can hide in the rocks, they can fix nitrogen, they can produce oxygen.
But
Pure.
here comes the but.
Do you know how long the Great Oxidation Event on Earth took?
Give it to me.
Hundreds of millions of years.
Oh, yeah.
And Earth had vastly better starting conditions. We had more sunlight, abundant liquid water on the surface, better baseline temperatures. Biology works on geological timescales. If we wait for bugs to make the Martian air breathable, we aren't talking about centuries. We're talking about eons, 10,000 to 100,000 years minimum.
So the idea of a green Mars, where I can take off my helmet and breathe the air in my lifetime, or even my great-great-grandchildren's lifetime.
It's a fantasy, unless we use heavy industry to do the work of biology, like building millions of giant atmospheric scrubbers that chemically convert the air. Creating a breathable atmosphere naturally is the longest pole in the tent.
This whole analysis is getting a little depressing, to be honest. I mean, every single solution has, but it takes a million years, but it requires a mirror the size of Texas attached to it.
It's not depressing, it's realistic. And it forces a pivot in our thinking. And this is where the conversation and the sources gets really interesting. Because if Earth 2.0 full true terraforming is impossible or just way too slow, what is achievable?
The pivot, redefining what success looks like.
Exactly. We stop aiming for full terraforming and we aim for partial terraforming.
What does that actually look like for a person standing on Mars?
It looks like a planet where you still can't breathe the air, but you don't need a spacesuit to walk to the grocery store.
Okay, paint the picture for me.
You use the limited resources we have to thicken the atmosphere just enough, maybe to that 10% or 20% level we talked about. That's enough pressure to stop your blood from boiling. It's enough of a physical barrier to block the worst of the cosmic radiation and micrometeorites. And it's enough to hold some heat so it's not minus 100 degrees at night.
So I walk outside my habitat. What am I wearing?
You're wearing a heavy coat because it's still fundamentally cold. You're wearing an oxygen mask or a lightweight rebreather because the air isn't breathable. It's still mostly CO2. But you aren't in a pressurized, bulky bubble. You aren't in a Michelin man suit. You have mobility. You can build things. You can drive.
That feels vastly more manageable.
It is vastly easier than a full terraforming, and it allows for domed cities, or my personal favorite concept from the literature, lava tubes.
I really want to talk about the lava tubes. I've seen some concept art for this, and it looks incredible.
The lava tubes are staggering. Mars has volcanoes that make Mount Everest look like a molehill. Olympus Mons is roughly the size of the entire state of France. When these massive shield volcanoes erupted billions of years ago, they created underground rivers of magma. When the lava drained away, it left these empty, hollow tubes behind.
Natural tunnels just sitting there.
Massive ones. We've seen skylights, which are holes where the roof caved in from our orbiters. Some of these tubes are calculated to be so wide you could fit the entire downtown city of Philadelphia inside a single tube.
A whole city inside a natural stone tunnel.
And they are already built. You don't have to construct the structural shell. You just have to seal the ends with airlocks and pressurize the inside. You have a natural stone roof that's tens or hundreds of meters thick, completely protecting you from radiation, protecting you from micrometeorites, and shielding you from the global dust storms. Plus, the temperature underground is constant. It doesn't swing wildly from day to night.
So the future of Mars isn't necessarily vast forests on the surface. It's thriving cities underground.
Or under massive glass domes nestled in deep craters. It's what the sources call a habitat alternative. And this leads to a really interesting cultural divergence that the authors dive into.
Yes, a philosophical difference between terraforming and adapting.
Right. Full terraforming is fundamentally about making Mars into Earth. It's imposing our will on the cosmos. It's saying, we want open skies, we want rain, we want to farm wheat in the Martian dirt, just like we do in Kansas.
It's colonization in the most aggressive sense of the word. We make the alien planet look exactly like us.
But the habitat approach, that is about humanity adapting to Mars. We live in domes, we live in the lava tubes. We look out at the beautiful, stark alien landscape through a visor or a window, but we don't destroy it. We live in an intimate relationship with a world that remains fundamentally undeniably Martian.
It's a very different philosophy. It's less arrogant, maybe.
Or just more pragmatic. It acknowledges our limits and accepts that we are the guests in this environment.
But this leads us to the final, and perhaps the most difficult, hurdle in all the source material. We've talked physics. We've talked massive engineering. Now we have to talk ethics.
The life variable.
We keep talking and assuming that Mars is just a dead rock, a fixer-upper waiting for tenants. But what if it isn't?
We haven't found life yet. But as we discussed with the radiation and the perchlorates, the surface is completely sterilized. If I were a Martian microbe, I wouldn't be caught dead on the surface. I'd live deep underground, down in those warm, wet, subglacial aquifers we just talked about.
So there could be an entire biosphere down there right now, a deep biosphere just quietly existing.
It is entirely possible. And if we start terraforming, if we change the global temperature, change the pressure, flood the entire planet with new, heavy greenhouse gases, what happens to them?
We kill them.
We almost certainly drive them to extinction. We alter their environment vastly faster than any organism could naturally adapt.
So the fundamental dilemma is, do we have the moral right to commit planetary genocide, even if that genocide is just against microscopic slime?
It's a really heavy word, but yes. If Mars has life, it represents what scientists call a second genesis.
Explain that concept for the listener.
Right now, we only know of exactly one instance of life arising anywhere in the universe, and that is Earth. We don't know if life is common, like cosmic mold, or if we are a freak mathematical miracle. If we find life on Mars, and it's genetically different from us, meaning it didn't just hitch a ride on an asteroid from Earth millions of years ago, then it proves that life arose independently twice in the exact same solar system.
Which would strongly imply the universe is absolutely teeming with life.
Exactly. It would be a most important paradigm-shifting scientific discovery in human history.
And our terraforming efforts would just pave over the evidence.
It would be like burning down the Library of Alexandria so you could build a parking lot. We would lose the opportunity to study and understand the alternate origins of life forever.
Are there laws against doing this?
There are planetary protection protocols. Right now, NASA has an actual Office of Planetary Protection. They make the engineers meticulously sterilize their rovers and spacecraft. They are terrified of contaminating Mars with Earth bacteria.
Because if we finally find a bug on Mars, we need to know if it's a true Martian or if it's just a stowaway from a clean room in Florida.
Exactly. But terraforming is the ultimate violation of those protocols. It renders them entirely moot. You are intentionally flooding the planet with Earth life. You are literally trying to contaminate it on a planetary scale.
And who decides if we do it? There is no unified Earth government. If a private company sends 1,000 rockets and starts dumping genetically modified algae, or if a single nation decides to start the greenhouse process, who stops them?
Nobody. There is no governance framework for this at all. It's the Wild West. The Outer Space Treaty of 1967 says you can't own land or put nukes in space, but it doesn't explicitly say you can't change a planet's atmosphere.
But let me play devil's advocate for a second here. What about the dead world argument?
Sure. If we search, and we search deep with specialized drills, and we find absolutely nothing,
If it really is just a sterile dead rock,
then the ethics simplify tremendously. Most people, even the strict ethicists in the source material, would argue that a living world is inherently better than a dead one. If it's sterile, we have a moral imperative, almost, to spread life, to wake the planet up, to create a backup drive for the Earth's biosphere.
but we have to be absolutely sure first.
And how can you ever be 100% sure you didn't miss a pocket of microbes somewhere deep in a microscopic crack 3 miles underground?
You can't.
That's the risk.
Wow. Okay, we have covered a massive amount of ground today. We've gone from the sci-fi dream of green valleys to the harsh, freezing reality of vacuum and radiation. We've looked at the missing gas, the missing magnetic shield, the completely impossible timescales, and we've looked at the ethical minefield of the deep biosphere.
It's a lot for anyone to process.
So let's wrap this up with a verdict. Based on everything in the Red Blueprint and all this research, is terraforming possible?
You want the honest answer.
I want the honest answer.
Full Terraforming Earth 2.0, walking outside in your shorts, swimming in oceans, breathing under blue skies is likely impossible, or at least impossible without technology that looks like pure magic to us today. The resource inventory just physically isn't there. But partial terraforming, creating a slightly warmer, thicker atmosphere, building a vibrant human civilization that lives in massive glass domes and pressurized lava tubes, that is probable. It is absolutely achievable.
It's not the paperback sci-fi cover art we grew up with, but it's a future.
It is a viable future, but remember the technology required. Even for partial terraforming, we need energy sources we haven't perfected yet. We need industrial capacities that dwarf the entire Earth's current economy.
So we aren't exactly doing this next Tuesday.
No, this is a project for our great-grandchildren's great-grandchildren.
I want to leave you, the listener, with a final thought on all this. We spent this whole time talking about engineering a planet. But maybe the real engineering project is us.
How so?
Well, the choice between terraforming Mars to look exactly like Earth or adapting ourselves to live within the limits of Mars, that's ultimately a choice about our own identity.
It really is.
Are we a species that just consumes worlds and forces them to fit our specific mold? Or are we a species that can learn and adapt and find a way to thrive in a place that is fundamentally different from where we started? What if the purpose of Mars isn't to be colonized and paved over, but to push human evolution into something entirely new?
Maybe the ultimate goal isn't to create a second Earth. Maybe the real goal is to create the first Mars, a completely new branch of human civilization.
A Martian humanity.
Exactly.
Well, that is a profound place to end our deep dive. Next time you look up at night and see that little red dot in the sky, remember, it's not just a rock, it's a mirror. It challenges us to see what we are truly capable of, and more importantly, what we are willing to become.
Beautifully put.
Thanks for analyzing this source material with me today.
Thanks for having me. It was fascinating.
And to you, listening, keep dreaming, but always keep checking the physics. We'll see you next time.